just went ahead and did this explore activity all together. So I'm just going to go ahead and project it. We'll talk about it. And then this one's going to be pretty handy just because it's one of those things where you can, in real time, visualize and see exactly what different values are doing different things to a graph. So first of all, a quadratic equation, standard form of a quadratic equation is right here. Y is equal to ax squared plus bx plus c. This is something that you saw back in algebra 1. And if you think back to unit 1 real quick, the value of a here in a quadratic basically does the same thing as the value of a that we saw back with both linear and absolute value functions. What did a do back in unit 1 at the beginning of a function? Anybody remember? A controlled a few things. If you go to the bottom of page 58 and the top of page 59. Bottom of page 58, top of page 59. Those two things kind of tell you what A does. And A does the same thing as it did back then. What was A in control of in a function? Yeah, the width. Dilation just means it's getting narrower or wider. And then at the top of page 59, what else does A control? Yeah, if there's a reflection or not. So here we go. A, if we make A larger, it gets narrower. If we make A approach 0, it gets wider. But then if it goes negative, well, if it's 0, then that means there is no squared, which makes it linear. But then if we go negative, it flips it upside down, reflects it across the x-axis. And as it goes further away from 0, it gets narrower. So that value of A does exactly the same thing as it did back in unit 1. The value of B, we haven't really looked much at that, but let's check out what B does. What does it appear is happening? What does it look like B is doing to the graph? Yeah, it's kind of shifting it left and right a little bit. No, it looks like it's moving it down to the left here and then down to the right here, but it's, you know, moving it left and right. And then what do you suppose C is going to do? Any predictions? A rotation? That's an interesting thought. However, if you start to rotate a quadratic, it ends up not being a function. But that's an interesting idea. We actually will see sideways parabolas later on in this class, not this term, but those would not be functions. They would definitely be relations, but not functions. Any other thoughts on what C might do? A rotation would be kind of cool, though. So we have the width up versus down. We had left and right. Hey, let's see if it moves it up or down. Ha, look at that. See, moves it up or down. So if we head on down here, a few questions. Question number 1, use the slider for A to manipulate it. What happens to the graph as the value increases from 0 to 5? It gets narrower. Okay. What happens when A is negative? Yeah, flips it upside down over the x-axis. So it reflects it across. Technically, we'd say it's a reflection across the x-axis. But if you just want to say it flips it upside down, that's fine. Exercise 2. For the value of B, first question here, what is the y-intercept of this function? Where's it cross the y-axis? At 1. So the graph crosses the y-axis at 1. All right. What happens to the graph and the y-intercept as the value of B changes? So if we move B and make it larger, it's moving it to the left, but what's happening to the y-intercept here? Yeah, nothing. The y-intercept is not changing as we move the value of B positive and negative. All right. So the graph shifts left and right, but the y-intercept stays the same. That's what we're talking about there. Exercise 3, value of c. What happens as we change c values? It moves it up or down. Exercise 4, for a quadratic function, the vertex will always be, oh, here we go, vertex. The vertex will always be the maximum or the minimum of the function. In this case right here, is the vertex right there, is that at the top or the bottom? It's at the bottom, so it's a minimum. What type of number is a here, positive or negative? Is a positive or negative? Positive. So if a is positive, it's facing up, which means that there is a minimum. If a is negative, now we have a maximum because it's upside down, because a is negative. So going back here real quick. For a quadratic function, the vertex will always be a maximum or minimum. Examine all the sliders to see which values affect whether the vertex is a maximum or minimum. There's only one value here that determines whether it's a maximum or minimum. Which one is it? A, B, or C? A. A determines whether we're going to have a maximum or minimum, because if A is positive, you'll have a minimum. If A is negative, you'll have a maximum. A is the only thing that determines whether or not you have a maximum or a minimum. And that's just based on whether it's positive or negative. How do you think you can determine whether a quadratic function will have a maximum or minimum without graphing? Look for the value of? What value determines whether it's a maximum or minimum? A. A determines whether it's a maximum or minimum. If A is positive, you have a minimum because it's a normal looking parabola. If A is negative, you have a maximum because it's upside down. So you can determine whether a quadratic function is going to have a maximum or minimum based on the number next to x squared, because that's A. If that number is positive, you'll have a minimum because it'll open upward normally. And if A is negative, it'll be upside down, which means that you'll have a maximum. How can you determine the end behavior without graphing? It also has to do with A. Because if A is positive, it's just a regular U-shaped graph. So end behavior would be up over here and up over here. If A is negative, it's going down over here and down over here. So like as x approaches infinity, y approaches infinity. As x approaches negative infinity, y approaches infinity. Now the end behavior of a quadratic as well always does the same thing on both ends. It's either both up or both down. It will never be opposite. Always doing the same thing on the ends. Last part here. We'll talk about that. All right. Let's get into the book. So, all right. Moving into some notes here. Everything that you're going to see is basically everything that we just talked about. And like I said, I'm planning on moving relatively quickly through these notes today, just because there's definitely a bunch of stuff in here you've seen before. I don't want to move so fast because sometimes it's hard to kind of like get a grip on things when you're in Algebra 1. So I don't want to move too fast in case you haven't really ever felt confident about this stuff before. But in general, today we're going to be graphing quadratic functions. Here's goals for graphing quadratic functions. And then this is going to be a new thing here, finding and interpreting the average rate of change of quadratic functions given symbolically in tables and in graphs. That sounds complicated. We got some vocab, quadratic function, axis of symmetry. We've seen that already with absolute value functions. Parabolas have them too. Vertex, we've seen that before as well. Maximum, minimum, we've seen those things before. Rate of change. What's another thing? What's another way of saying rate of change? Who said slope? Yeah, slope. Rate of change is the same thing as slope, which is a little bit of a weird thing to think about when you think about a parabola, because parabolas don't have slope because they're not lines. But we are going to be talking about rate of change and average rate of change as they apply to certain portions of quadratic functions, even though quadratic functions don't have slope. I want to make that perfectly clear. Parabolas do not have slope because the only thing that can have a slope is a line. That's not a line. But we'll get into that as we go through this lesson. So here we go. Graphing quadratic function. A quadratic function has an equation of the form y is equal to a times x squared plus b times x plus c. It will always have a squared. No matter what, you will always have a squared in a quadratic. You will not always have a b value or a c value, because if you look here, it says a cannot equal 0. Because if a is 0, then there is no x squared, which means it's not quadratic. It would just be linear at that point. It doesn't have any restrictions about b or c being equal to 0 because they can equal 0, but a cannot equal 0 if it's going to be quadratic. So we have three different terms. We have the quadratic term, the one with the squared. We have the linear term, the one with just the x. And then we have the constant term, which is the one that doesn't have a variable. By the way, c is also the value, the constant term. This is equal to the y-intercept. The value of c is always where the graph crosses the y-axis every single time. That is something that you learned in Algebra 1. This is a reminder on that. And it even says that on this graph right here, y-intercept is c right there. So just like when we were graphing absolute value functions, it's a good idea to know where your vertex is. You could just create a general table of values, -2, -1, 0, 1, and 2, and kind of start your graph with that. But again, if you don't figure out where it turns around and goes back up, or turns around and goes back down if it's upside down, it makes it a little bit more challenging than it needs to be, and your table can become a lot larger than it should be and all that. So just like with absolute value functions, where we took the stuff inside the absolute value, we set it equal to 0, and we solved for x. That gave us the x value of the vertex for an absolute value. There is another way that we can figure out the x value of the vertex in a quadratic as well. And this is also something that you saw in Algebra 1, and you might not remember it necessarily, but it says, here we go. Key concepts. These are the basics of kind of building a quadratic on a graph. The first thing is the y-intercept is c. That last number by itself is where the graph crosses the y-axis. If there is no value of c, that means the y-intercept is 0. The axis of symmetry is the middle of the graph. It is where the vertex is located, and it's always defined by the x value of the vertex. And so if you were trying to figure out where that is, the x value of the vertex, which is also the axis of symmetry, is equal to the opposite of whatever b is divided by 2 times a. The opposite of b divided by 2 times a. That's where the middle of your parabola is on the x-axis. Now, if you want the vertex, you would take whatever you get for here. That's your x value for the vertex. And then you just plug it back in here and here for x into the function to get the y value of the vertex. And that'll tell you exactly where it is. The axis of symmetry intersects the parabola at its vertex. So the x-coordinate of the vertex is the opposite of b over 2a. So it tells you where the middle of the graph is. Question over the side here. Why is it important to know whether the vertex is a maximum or minimum when you're graphing? Why would it be important to know if it's a maximum or minimum when you're graphing, even before you graph? Yeah, you have an idea about what it looks like before you put it on a graph. If a is negative, you go, oh, okay, well, it needs to be upside down when I graph it. Therefore, if I graph it and it's not an upside down parabola, something went wrong. You will derive the equation for the axis of symmetry in lesson 3-5. Ooh, fun. Derive means you're going to come up with it. So we'll see that when we get there, though. All right, down here, maximum or minimum values. We talked about this in the warm-up. The vertex is either the highest or the lowest point. It's either a maximum or a minimum in a quadratic. The graph of a function where a is not equal to 0, because it has to be quadratic, and a is 0, it's not quadratic, opens upward and has a minimum when the value of a is greater than 0. If a is greater than 0, it's a normal U-shaped graph, which means the vertex is at the bottom, which makes it a minimum. If a is less than 0 or negative, that means it's reflected over the x-axis, which means it's upside down, and the vertex is at the top, making it a maximum value. So, also, over here, just because the vertex is a maximum does not mean it's going to be located above the x-axis. I mean, it could be Could be like that. That's a function. That's a quadratic parabola with a maximum value, but it doesn't go above the x-axis. So just because it is a maximum value does not mean that it's going to be above the x-axis. And by the way, this is the reason why it's saying this is because when we start solving these, it's going to be important for that. And just because it has a minimum doesn't mean that the vertex is going to be located below the x-axis. It could be above the x-axis. So it just determines the direction, facing up versus facing down. All right, turn the page. Let's go ahead and do some graphing. Example 1 says to graph this. And, oh, hey, look at that. Look what we're bringing back, domain and range. So all that stuff that we talked about in Unit 1, that tour of all of the things algebra, basically, Algebra 1 is just like all these random topics. What are we doing with them? Well, they come back over and over and over. And domain and range is something that will come back over and over and over. So the first thing we're going to do is decide the values of a, b, and c. If there was a number next to x squared, what would it be? 1. So a is 1. What's the value of b? 2. What's the value of c? -3. All right. So since c is the y-intercept, that means the y-intercept is -3. All right. And then to figure out, so first thing you're going to do basically is figure out where the y-intercept is, because that's going to be the easiest part to pick out because it's always the number that's by itself with no variable. Then figure out where the axis of symmetry is, which is also the x-coordinate of your vertex. And if you take the opposite of b, since b is 2, the opposite of b would be -2. Now the negative can go off to the side. It can also go on the numerator as well. So if you want to do this, or -2 over 2 times 1. This is probably how I would write it. I put the negative on the numerator as opposed to just off to the side. So the opposite of b, since b is 2, we got -2, over, there will always be multiplication of 2 on the denominator because that is part of this little formula. 2 times the value of a, and a is 1. So that's just -2 divided by 2, which is -1. So that means the equation of the axis of symmetry is x equals -1. Which also means that the x-coordinate of the vertex is -1. And the last thing we're going to determine before we actually start plotting points is determining what the vertex is. Is it a maximum or a minimum value? So because a is greater than 0, a is a positive number, it opens up like a normal U, which means the vertex is a maximum or minimum. Minimum, it's at the bottom. So I'm just going to write min for minimum. And then we've got ourselves our table of values here. And you'll notice that the vertex is the point in the middle of the table. Vertex will always go in the middle of your table. And just like I've been showing you as well, if you pick 2 numbers below the vertex on the x-axis and 2 numbers above the vertex on the x-axis, that'll get you nice symmetrical points around the axis of symmetry. So let's start here with the vertex. If we plug in -1 for x, what is -1 squared? 1. What's 2 times -1? -2. What's 1 minus 2? -1. What's -1 minus 3? -4. So the vertex is at -1, -4. Hey, look at that. It's right down there. It's already there. We also know that the y-intercept is at -3, and a y-intercept always has an x value of 0. So 0, -3. That's right there. Now, in terms of where the other side goes, -2 is 1 away from -1. 0 is also 1 away from -1. Those two values, just like in absolute value functions, have the same y value. So 0, -3, -2, -3. No math required. And then if we use 1, let's just do 1 here. If x equals 1, wait a second, that should be a 1. Not a -3. Hang on. All right, 1. Because the -3 is up there. The 1 should be here. That was the typo. If we plug a 1 in, 1 times 1 is 1, 2 times 1 is 2, 1 plus 2 is 3, 3 minus 3 is 0. So we get 1, 0, and negative 3, 0, which are these points right here and here. Which, by the way, foreshadowing, those are the solutions to this function. Because the x-intercepts are the solutions. X-intercept, solution, zeros. So once we start solving quadratics, we're looking for where the quadratic crosses the x-axis. In this case, it's negative 3 and 1. That's how you can solve it by graphing. Graph it, figure out where it crosses the x-axis. We'll do that in a later lesson. All right. So we've graphed the parabola. Now, we have to talk about the domain and the range. Every single parabola on the x-axis goes forever in both directions. Meaning that the domain of every single parabola is what? All real numbers. So you could do, there's quite a few things you could say to do this. You could just say, that's the algebraic notation. That's the symbol for all real numbers, the double vertical line, capital R. Or if you want to, you could go with interval notation. Negative infinity, infinity with parentheses. Or if you want to, you could use set builder notation, which is using for the range over here. Set builder would be braces, x, all values of x, such that x is an element of the real numbers. That would be our set builder notation. So you have three. You have algebraic, you have interval, you have set builder. Those all say the same thing. If it doesn't tell you what form to use, choose whichever form you want. Yeah. You could use the words all real numbers as well. Yeah, that would be the same as the algebraic notation. Yeah. So instead of using the symbol, if you just want to write all real numbers, that's fine. By the way, we did this exact kind of stuff in unit 1. So what's the range of this function? All y values, all values of y, such that y is greater than or equal to what? Negative 4. Why? Yeah, it's the minimum. That's as far down as it goes. Every other value of y is above that or equal to that. So that's it. Or if you want to just go with algebraic notation, you would say y is greater than or equal to negative 4. Or if you want to go with interval notation, you would say bracket negative 4, comma, infinity, parenthesis. So those are your three options in terms of how to write the range. Because we have three forms of that. All right. Moving right along. Comparing quadratic functions. Let's see. Compare the graph of f of x to a quadratic function with a y-intercept of negative, to a quadratic function g of x with a y-intercept of negative 1 and a vertex at 1, 2. Which function has a greater maximum? You had a question almost just like this on your unit 1 test, actually. Except which one, it said like which one has the lesser minimum. You're looking at which one has the greater maximum. So let's just walk through this one real quick. By the way, we could probably answer this question without doing any of this work. Because if the vertex is at 1, 2, now we don't know anything really about g of x in terms of what the a value is, because I don't see a function there, but we'll see what happens. Okay. From the graph f of x, it appears to have a maximum of 5 because the vertex is right here at the point 3, 5. So 3, 5. And the axis of symmetry is x equals 3 because that's where the x value of the vertex is. No, I guess it's implying that 1, 2 is the maximum here because it says which one has a greater maximum. So I guess they're both facing upside down. All right, the y-intercept of this function is what? Of f of x. Oh, hold up. No, it's talking about g of x now. Let me go back. 1, 2. Sorry about that. This is at 1. I glossed over this graph g of x situation. So everything else from here on down is about g of x. All right, 1, 2. So we're just going to graph this function down here. Sorry, 1, 2. That's the middle of our graph there. I mean, we already have the answer. We know which one goes higher. But let's just go ahead and get this on here anyway. The y-intercept is at negative 1. So we have the point 0, negative 1 on the graph. on the graph here. So let's see. If you go to 0, -1, that's here. Which means that if you go 1 to the right of the vertex as well, you have another point with the y value of -1. So that would be the point 2, -1. You can reflect that. Now, I don't like the fact that we only have 3 points here. Usually we should have 5, but we don't have enough information to get a couple other points on there. So connect the points with a smooth curve. Now, when you graph a parabola, I would not recommend starting to the side of it and then drawing all the way through the vertex. I actually start at the vertex most of the time because it allows me to kind of get the shape of the curve, because otherwise it can look very absolute value-like. And it can look kind of pointed at the end, but with a parabola, we don't want a point at the end. We want a curve at the end. And then once you kind of get that shape around where the vertex is, then you can extend it. Let's see. 2 is the maximum. So which one has the greater maximum, f of x or g of x? Which one has the highest y value? F of x, yeah. Now, you didn't actually have to do all that work to figure that out, because if we know that the vertex is the maximum, that means that 2 has to be the maximum. This one clearly goes higher than 2. So we could have just looked at the initial problem and said, f of x has the higher maximum. But in terms of graphing, it's never a bad idea to get a visual. All right, example 3. The ski resort. Now, this is an interesting question. I like this question a lot, actually. And coming up with the quadratic function for this is not a super easy task. So let's talk about this one. A ski resort has extended hours on one holiday weekend per year. Last year, the resort sold 680 ski passes at $120 per holiday weekend pass. Okay? This year, the resort is considering a price increase. They estimate that for each $5 increase, they will sell 20 fewer holiday weekend passes. How much should they charge in order to maximize? Maximum. What does that suggest about our parabola? Which means the value of A is negative. Good. How much should they charge? So we're looking for an actual amount. If they're charging $120 currently, we want to know exactly how much they should charge to maximize their profits. So I just want to kind of set up the scenario for everybody, and then we'll get into the details about let X represent and all that. So I'm just going to grab a calculator real quick. How can we find out how much money they made on holiday passes from the previous year? Because in order to figure that out, it'd be good to have a comparison of how much money they made last year versus how much money they're expecting to make this year. So how can we find out how much money they made last year? Yeah, multiply the number of passes by the cost per pass. So it'd be 680 times 120. So for the holiday weekend passes, they sold 680 of those at $120 each. So from the holiday weekend passes, they made $81,600. Now, what they're saying is, if we increase the cost by $5, so let's say 125, how many skiers will they expect to see if they increase it by $5? For every $5 increase, what's happening to the amount of passes? 20 fewer. Yeah, they're expecting 20 fewer to be purchased, because as you increase prices, fewer people are likely to buy it, right? So if it's $125 a pass, how many people would be buying the pass then? 660, because that would be 20 fewer than the previous year. So 660. So they could expect $82,500 if they increased it by $5. Now, you also might think it works the other direction, right? Maybe they'll make more money if they decrease the price because more people would buy the pass. What if we went the other way for a second? What if we said, all right, $115 a pass, which would mean it wouldn't be 20 fewer people. You might expect that 20 more people would buy it, which would be 700 people, right? And that's 80,500, which is less than what they made this current year. So a price decrease is not ideal. Now, a $5 price increase is going to get them about $900 extra. What if it went to $130? How many people would you expect to buy if it went to 130? Be 20 fewer than that. 640, okay. So every $5 increase decreases the amount of people by 20, but look at that, it's still going up, 83,200. What about 135? How many people? 620. 83,700, still going up. Now, you'll notice that these increments of increases are not linear, right? It went up by 900 the first time, and then it went from 82,500 to 83,200. That's a $700 increase. And then 83.2 to 83.7, that's a $500 increase. So every time they're adding price, it's not increasing like this, it's kind of doing this. It's like, oh, okay, we're getting a little bit like the profit is kind of like shrinking, not in terms of like shrinking, but like it's becoming less of a gap between the costs here. What about $140? How many people? 600. 84,000. That's another $300. What about $145? 580. That's another $100. So 84,100. What about $150? 560. Oh, it went down. Okay. So we found the answer to this question, by the way, just by doing all that. But we're using that pattern. Everybody kind of see the pattern? $5 here, 20 fewer people here. So what we're going to end up doing is, now that we kind of understand how this is going, right? It's going up, it's going up, it's going up. We hit the peak, which is going to be $145 a ticket and 580 people, and it's going to earn them $84,100. But after that, the amount of money they're earning is actually going to start to go down a little bit because they end up charging too much. So let X represent the number of $5 price increases. Okay, so every $5 increase, you would expect 20 fewer people. Let P of X, this is Y, let the Y value represent the total amount of money. So X is $5 increases, Y is total amount of money. We already worked that out with this. P of X, the Y value, the amount of money they're going to earn is equal to the price of each pass. So the cost of the pass here was $120. And then we added $5, and then we added 10, and then we added 15, then we added 20. So they were $5 increments. And then we had multiple increments. Now, the number of $5 increases, it tells us that what X is. So if you increase it by one $5 increase, that would be an increase of $5. If you increase by two $5 increases, that's a $10 increase, and so forth. And the total number of passes sold is going to decrease by 20 people for every $5 increase, starting with how many people initially? 680, because that's how many passes they sold last year. Now, if you multiply the cost of the pass times the number of passes sold, that will give you the total amount of money earned. So here it is. That's the cost of the pass right there. This was the 125, 130, 135, and so forth. This was the 660, 640, 625, 80 numbers, all that. And that's how we can calculate those. Now, how do you get from here to AX plus BY equals C? Because this is not AX plus BY, AX squared plus BY plus C. Sorry, I keep saying Y. AX squared plus BX plus C. Anyway, what process can we do to multiply out these two sets of parentheses? Anybody remember? FOIL. Yeah, first outer inner last. So we're going to do FOIL here. We're going to multiply 120 times 680. That's how much money they made last year. We already know that number. I'm going to go up. That was $81,600. And then the outer values, 120 times negative 20x. That's this one right here, negative 2,400x. And then the inner values, 680 times 5x. So that's 680. Oops, clear. No. 680 times 5, 3,400. So 3,400x. And then the last values would be negative 5x times negative 20x, or sorry, 5x times negative 20x. And that's this minus 100x squared. Now, this isn't quite in standard form because we need the x squared term first, which is a negative 100x squared. There it is, negative 100x squared. Hey, and there's a negative a value, which makes sense with how we were thinking about it. It's upside down. Maximum value at the top. And then the two terms in the middle we can put together because they both have x. Those are like terms. So 3,400 minus 2,400 is what? 1,000. So 1,000x. And then the plus 81,600 is the value c. So that right there, that's our y-intercept. But really what we're doing here is we're going to take this function and we're going to look for the maximum value. The maximum or the minimum is always what point on a parabola? The vertex. So we don't need to graph this. We just need to find the maximum value, which is always going to be the vertex, or the minimum value, which is always going to be the vertex. So we're going to use the formula to figure out the vertex. We're going to get the axis of symmetry first, or the x value of the vertex. Opposite of b divided by 2 times a. b is 1,000. The opposite of b is negative 1,000. Divided by 2 times a. A is negative 100. So this is going to equal negative 1,000 divided by negative 200. What does that equal? What is it? 5. So that means that the vertex has an x value of 5, which means there should be how many price increases? 5. How much is the value of each price increase? How much is it going up by? Each price increase goes up by how many dollars? $5 each time. Okay. So that would be a total increase of how many dollars? $25, which would be a total price of $145. And that's interesting because that's the exact number we got for what they should increase the price to. So they increased it 5 times at $5 a piece. So they increased the price by $25, which means they should increase it to $145. So if you find the domain here, by the way, what would the domain of this end up being? Any thoughts on that? Is it going to be all real numbers? No. All real numbers doesn't really make sense. Why not? What's that? Yeah, they're not going to do negative money. They're also not going to do negative price increases, right? So the domain is going to be, x is going to have to be greater than or equal to 0 because they're definitely going to raise the price. So, well, maybe they won't definitely raise the price. Maybe they won't raise the price, but they're not going to decrease the price. How about that? So an x value, remember, that's number of price increases would be the x. So they're either going to leave it the same, that would be 0, or they're going to increase the price. Now, how many price increases could they do until they're not making any money? That's the question. What's that? So 5 is going to be the maximum. Now, that'll definitely decrease it, but it's not going to make it go to 0. Like, how many price increases would they have to do until they're not earning money is the question. You just kind of have to like figure it out, right? You'd have to plug in a bunch of options and see what happens. If you were to do a whole bunch of them, I'm just going to go ahead and look at my teacher's key right here. It's 34. 34 price increases. So basically what we're saying here is that if you do 34 price increases, you're increasing the price by $170. And so if you add that to the initial 120, that would be a $290 price of $290 price of the ticket. Now, if 680 people bought last year and it's decreasing by 20 for every price increase, that means that 0 people would buy it if it went up to $290 a ticket. So that's why it's 34. Because if nobody buys it, there's no point in doing this in the first place. So the actual domain is going to be between 0 and 34. Now, in terms of what it should be, like we know what they should sell for. And so that's what we're going to be talking about here. The range. What's the least amount of money they can make? What's the least amount of money a company can make? 0. What is the amount of money they will make if they sell tickets for $145, the maximum price? Maximum price of the ticket in terms of how it's going to work out will get them the maximum profit. We saw that on the calculator already. It was $84,100. And because it can't be negative, right? The parabola would definitely go into the negatives, but based on the situation, we can't have it negative. All right, so what does P of 5 mean instead of P of X? What does P of 5 mean instead of P of X? X is 5, yeah. So that would be the maximum amount of $5 increases, which is 25. So it's just saying the maximum amount of money generated, that is the maximum value here for Y. So that's 84,100. There we go. So we're going to do another one, but it's going to be real quick because it shouldn't take, now that you've seen the process, I don't think it's going to take that long to do this one. So last year, a ticket provider sold 1,350 lawn seats for a concert at $70 per ticket. They're considering a price increase. It's the same scenario. So what I want you to do is get a calculator and work this one out. See what you come up with. Let's go with 3 minutes and see how you do with 3 minutes on this. So try to get it done quickly. Go ahead. I'm going to use the margin over here onto the right to do the work. So I'm going to move it out of the way while I work on it, and then I'll bring it back in a couple minutes and take about 3 minutes, see what you get. Okay. If you're not done with everything, that's okay. But does anybody know how much they should sell each ticket for to maximize profit? Or how many price increases they should do? How many $2 price increases should they do? Somebody get that? Or the total price, Lily? I think I saw your hand up there. $80 is the answer for total price. Good. So the function is over here. So they sold for $70, and they're looking at increments of $2 increases here. And then they sold 1,350 tickets last year. They're expecting 30 fewer people for every $2 increase. So it's the exact same setup as the last problem. And so then if you multiply everything out using FOIL and you rearrange it to get it in standard form of a quadratic, you get y equals negative 60x squared plus 600x plus 94,500. It's important to get this because from here you can figure out the x value of the vertex, which will be the point at which the maximum exists, which will tell you how many $2 increases to make. So if you say opposite b over 2 times a, you get 5. Question, Julia? So the maximum value should be 96,000. Did you get 5 for x? In terms of the number of increases? What's that? 2 each time. Oh, so you did the 2, 2, 2, 2, 2. Okay. That should get you to the same place. So did you get an $80 ticket for the maximum price? Yeah. So $80 ticket would be 5 increases of 2, which means that you would have 5 decreases of 30 people. So that would be 300 fewer people. So it would be 1,050 people times 80, right? So 1050 times 80. No, that's not right. Sorry, that's 150 fewer people. 1,200 times 80. Yeah, 96,000. So it'd be 1,200 people instead of 13,000. Or sorry, 1,200 people instead of 1,350. I would recommend instead of you can use that method, Julia, but I would recommend just kind of go ahead and setting up the quadratic function like we have here. So that would be my recommendation, is to write the equation for the quadratic like this. And then getting x, which if you get x, you're going to say it's equal to the opposite of b divided by 2 times a. Do a little multiplication, a little division, x equals 5. So that'd be 5 increases of $2 each, which means you're increasing the total cost of the ticket by $10 from the original price of 70. So it's going up to 80. And then if you have 5 increases, you would plug in 5 for x here, just like we did in the last problem. That would tell you the maximum amount of money, which would be $96,000, which will be useful for figuring out the range for sure, because the maximum amount would be 96,000. Now, this number 45 wasn't a lot of explanation on how to get that. But 45 basically means how many increases do you need until there are 0 people showing up, right? Until there are no tickets that are being sold. So if you think about it for a second, this part of the function here has to do with number of people, doesn't it? This is the number of people. So if this equals 0, the x value would tell you how many $2 increases you would have to do in order to get 0 people showing up. So if you set that equal to 0 and solve for x, that would tell you that there's 0 people showing up, and x equals 45. So 45 $2 increases, which means if you increase the price by $90 for a total of $160 a ticket, so if you charge $160 for the ticket, no one's going to show up. It's too expensive. So the domain is kind of an interesting one to figure out there. But if you think about no people showing up, that's this one here. Because the y value would be 0. You're not making any money if nobody shows up. I guess, yeah, so this would be 0 here for that. Any specific questions on this before we continue? We're going to look at something a little bit different on the next couple of pages, which will be, I think, simpler than what we just did here. This right here, I think, is the toughest part of the lesson. All right, we got about 20 more minutes, which is great. That'll give us plenty of time to finish this up. These pages are pretty big in terms of what's going on here, but like the idea is actually, I think, not super challenging because you're going to see something real familiar as we do this next part. So we're going to find and interpret the average rate of change. A function's rate of change is how a quantity is changing with respect to a change in another quantity. What's happening to x as y changes, or what's happening to y as x changes? In terms of a linear function, rate of change would be slope if it was linear. These are not linear though. However, for nonlinear functions, the rate of change is not the same over the entire function, right? It's steep and then it gets shallow and then it actually goes negative. So the rate of change is not constant in any shape. However, you can find the average rate of change if you focus in on a smaller part of the function. So if you don't look at the function as a whole, and you look at just like, hey, let's look at the values between here and here, what's the average rate of change? And so the average rate of change of a function f of x is equal to the change in the value of the dependent variable y. Dependent variable is y. The change in the dependent variable, this would be like a y value minus another y value, f of b minus f of a, y value minus a y value, divided by the change in the value of an independent variable, which is an x, over an x value minus an x value, over the interval ab. This is an interval notation. We're including a and b. That's why the brackets are there. What does that look like? That looks like the slope formula. That's because it's the slope formula. That is literally the slope formula written as a function of b minus a function of a. So y2 minus y1 over x2 minus x1. So this is the slope formula. So I'm going to write or y2 minus y1 over x2 minus x1. It's the same thing. So basically what you're doing is you're saying, all right, let's look at a couple of, like 2 points. We'll put boundary points within this parabola. And we're going to imagine for a second that if we were to think of this as a linear function for a second, what's the average rate of change between here and here? So for example, let me go back and show you a graph. So this first one here, if we said, okay, between 0 and 1, what's the average rate of change? We know it's a nonlinear function, but we're basically saying, imagine it was linear for a second between these 2 points here. What would the average rate of change be? And we'd say, okay, it's 3, because it's up 3 and over 1. We're basically making a slope from something that doesn't have slope. That's it. So average rate of change between here and here would be -1, down 1 over 1. Average rate of change between here and here would be 1 because it's up 1 and over 1. So you basically just pick 2 x values, find the corresponding y values, and basically create a slope from something that doesn't actually have slope. And basically saying, hey, if this had a slope, the slope would be this, which in terms of a nonlinear function, we call average rate of change, but it's the same formula. So that's the nice thing. So here we have determine the average rate of change from an equation. And we're going to determine the average rate of change for this function here over the interval from -4 to +4. So between -4 and +4 on the x-axis, what is the average rate of change? So this is what we're looking at. F of 4, basically the y value when x is 4, minus the y value when x is -4, over the actual x values of 4 minus -4. So that means we need to actually calculate the y values. How do we calculate the y value when f is equal to 4? Or not when f is equal to 4, when x is equal to 4, how do we calculate the y value? If we have this equation here. Yeah, plug 4 in for x. That's it. We're just substituting and solving. So if x is 4, instead of f of x equals -x squared plus 2x minus 1, we're saying f of 4 is equal to the opposite of 4 squared plus 2 times 4 minus 1. Notice that this negative is not inside the parentheses. And I shouldn't have said negative x squared. I should have said the opposite of x squared, because those words matter and they are not the same. The opposite of 4 squared is different than negative 4 squared. Negative 4 squared is 16. The opposite of 4 squared is negative 16. So this is negative 16 plus 8, which is negative 8, minus 1, which is negative 9. Negative 16 plus 8 minus 1 is negative 9. Then we're going to take the opposite of negative 4 squared. Negative 4 squared is 16. The opposite of that is negative 16. Negative 16 minus 8 is negative 24. Minus 1 more would be negative 25. Oh, hey, there's those numbers right there. Look at that. Negative 9 minus negative 25. That's negative 9 plus 25, or 25 minus 9. What's 25 minus 9? 16. 4 minus negative 4. 4 plus 4. 8. What's 16 divided by 8? 2. So the average rate of change over the interval of negative 4 to 4 is 2. I want you to try this one. And I actually think using just straight up algebra and the functions to do this is probably the most challenging way to do it. The last few examples we have, I think, are a little bit easier, because we'll be able to use the graphs and just kind of count up and over and all that. So try this one, take a minute or two on that, and then we'll keep going. On the inside of the car, because negative something, but then the other negative. So the type of thing how effective it is. That means however. Yeah, right. All right. How do we do? Negative 5. Should just be exactly negative 5. If you plug in 5 for x, 5 squared is 25. 25 times negative 2 is negative 50. Negative 5 times 5 is negative 25. So negative 50 minus 25 is negative 75. Plus 7 is negative 68. If we plug in negative 5, negative 5 squared is 25 times negative 2 is negative 50. So either way, this first term is going to be negative 50. Over here, negative 5 times negative 5 is positive 25. So negative 50 plus 25 is negative 25. Negative 25 plus 7 is negative 18. So we take negative 68, we subtract negative 18, or add 18. Adding 18 to negative 68 is negative 50. 5 minus negative 5 is the same as 5 plus 5, which is 10. Divide negative 5 to the average rate of change. So there's a lot of just substituting in and solving. Feel free to use your calculator to do this if you want to. In fact, you could just type in this whole thing. If we want to use negative 5, you say negative 2 parentheses times negative 5 squared minus 5 parentheses times negative 5 plus 7. There it is, negative 18. You can just dump it right into the calculator and it'll do the work for you. All right, next, example 5. Find the average rate of change from a table. All right, this time we're going between negative 3 and positive 3. Well, here's the nice thing about this one. We already have the values for x and for y, which makes this one a little bit easier. So f of 3 is negative 24. F of negative 3 is 48. And then it's the same process again. So negative 24 minus 48 would be what? Negative 72. 3 plus 3 is 6. So that's what? Negative 12? Yeah, all right, negative 12. Cool. No. Nope. It's just that's just the like algebraic notation to do that way, but no, you don't have to do that. All right, let's do the next one. Check step. All right, this table, okay, so we're finding the average rate of change between 2011 and 2015. So, you know what? I'm not even going to write out these numbers again. I'm just going to type it in on my calculator because I don't want to write those numbers out. So here we go. You ready? I'm just going to do the whole thing as an entire fraction on the calculator. So I'm going to open up a fraction. And I'm going to type in 1,924,436. Just make sure the numbers are correct. Minus 1,623,112 over 2015 minus 2011, or if you just want to type in 4 for the denominator, that's fine too. But the answer is 75,331. There we go. So it wasn't increasing by the same amount every year, but on average, it was increasing by 75,331 people a year over those 4 years. That's what we're saying. So from 2011 to 2015, the number of students taking the ACT, did it go up or down? It went up. It rose by an average of 75,331 students per year. You're just turning nonlinear basically into linear. That's kind of the idea behind it. Next, same thing again. Here we go. The graph shows the amount of money in the United States has spent on sports footwear since 2005. Use the graph to estimate the average rate of students spending on sports footwear from 2005 to 2015. So, years since 2005, that would be 0, 15.72. And then 2005 to 2015, that would be 10 years after. So that's this point here. It even tells us. That's nice. So we're just going to go ahead and do the thing again. So the change of values. Okay, the change in the y values is approximately 5.5 because 15.72 up to 20.99. If you subtract those, you get about 5.5. And the change in x values is 10 because it's an increase of 10 years. What's 5.5 divided by 10? It's 0.55. Which means that the average rate of change, algebraically, is 0.55. It's the same thing. So if we interpret from 2005 to 2015, the amount of money spent on sportswear in the United States rose, because it went up, it's a positive slope, by an average of, these are in billions of dollars, so 0.55 times, actually, we'll just say 0.55 billion dollars. You can just write it in decimals in billions. Now, if you want to, you can multiply it by a billion. 7, 8, 9. That would be $550 million a year. Or 0.55 billion. All right, we're just going to stop there. We're not going to bother with this last question. Okay, you do have an assignment. So sad. This one will not be due on Monday, though. Even though we are going to do a lesson on Monday, I'm going to have quite a few questions for you to work on here. So, we're going to do 1 through 45 odds. So a decent number of questions. This will not be due on Monday. It'll be due on Tuesday at the earliest. I will take questions on Monday, but don't worry about getting this done by Monday. All right. By the way, Monday's lesson, much shorter than this one here. So, and it also used graphing calculators and things like that. So it'll be less overall work too. All right. Come get graph paper if you need it, because you will need to make some graphs. And the bell will ring any moment.